And we wanted to know whether you needed those fully connected interactions to have this emergent gravity come out. I won't really explain why we're asking that question, but that was a question that we were asking. This is a question Lenny and I were discussing. And this is partly motivated by the question of whether we could modify the spectrum of operators in SYK, because SYK is a relatively dense spectrum, and you might, for gravitational applications, want to thin the spectrum out a little bit. You may have heard the statement before that holographic field theories have a sparse spectrum of operators. It's a different notion of sparsity, but we were sort of hoping that maybe this sparsification could get towards that. It turns out that doesn't seem to be the case, but nevertheless, one of the main conclusions of our work is that this sparse model that I'll define shortly does have emergent gravity. And what I'll give for evidence for that is really a path integral argument and some numerical evidence. But as I hinted at before, the operator spectrum includes the full content of SYK plus more. Okay, so we actually get more stuff rather than less stuff. Yeah, so that's one motivation. And the precise reason why you might care about this is because if you wanted to, say, simulate the SYK model or something related, like on a quantum computer, that's big business these days, you might want to know what's the simplest or most efficient program that does that simulation. And it turns out that these fully connected models, these all-to-all models, are actually pretty expensive to simulate. So here I'm showing you the previous, the world record, the best current algorithm for simulating fully connected SYK with 4-body interactions. And you see that if you want to simulate time evolution for a time t, then you need to measure time in units of j, that's the coupling. And the cost per unit time scales like n to the 7 halves. Yeah, it's it's polynomial in n, which is, we're told, good, but it's still rather expensive. So if you wanted to even, say, do 100 Majoranas, the people in this paper, Babish, Berry, and Nevin, estimated you might need on the order of 10 million of some non-trivial gate, which is a lot. Okay, we're a long ways from that. But it turns out that this sparse model.
Bosonic gates.
Sorry?
Bosonic gates is the bosonic qubits that you're simulating on.
It's the gates. So, the number of qubits is not so much bigger than the number of fermions, but you need a lot of gates because you have to Jordan Wigner all these different things, and it's quite complicated. Yeah, so it's pretty deep circuits to do the simulation. But
so is most of that n to the 7 halves from the fermion encoding?
No, actually, most of it is from the all-to-all. So you would only lose, I think, okay, I'm not 100% sure about this on the fly, but I think you'd only lose 1 power of n from if it was bosons or spins. So a lot of it comes from the fact that in these simulation results, this is just an interesting aside, what matters is typically the L1 norm of the Hamiltonian. But these couplings are normalized to make the L2 norm look nice. If you think about it for a second, you can get the normalization by making sure that the trace of h squared is extensive. But somehow that's not, the current algorithms can't guarantee good results if you only normalize that way. So you need, actually, there's sort of a cost which scales with the L1 norm, which grows with n. And that's, as far as I can tell, the source of this. Basically, there's a lot of terms in the Hamiltonian, and the cost of simulating those terms scales in an unfavorable way with n. But in this sparse model, it'll turn out that the number of terms is proportional to the reason you could actually get away with a much less costly simulation. So there'll be a parameter k that I'll define shortly, which is basically proportional to the number of terms. I mean, it's a constant, which is the ratio of number of terms to number of fermions. So just think of it as like an order 1 number. And now in this model that we'll define, the scaling goes like n squared instead of n to the 7 halves. And now this n log n is the fermion encoding. If you didn't have that, it would just be proportional to n, if it was, say, a spin model, which is the best you could do. So it's rather more efficient. You could shave off thousands of gates per time step, like a factor of 1,000 in the gates per time step relatively easily. And also I would point out that this result of Babish, Berry, and Nevin was for the q equals 4, the 4-body interacting case. If you increase q, you get a higher power of n here. But actually in our situation, you can increase Q without increasing the powers of n. So as you make Q larger, it becomes more and more efficient. And it's also actually possible, because of the sparsity, to do classical simulations much more easily with large numbers. So I'll show you results for 52 fermions, which, while we were working on this, was a world record. Recently, there was a bigger simulation done with a fully connected model, but it took many hours of computer time. And these results are actually not too hard to get, even on a laptop. So there's opportunity here just for classical simulation. So if you're interested in some model and you want to do a big size sort of Krylov-like study of it, it could be helpful just to sparsify it to give you some sense of what's going to happen. And the other motivation, which is still very much work in progress, but I can tell you the motivation at least, is having to do with codes. So a lot of with quantum error correcting codes. So to me, there's this, we're familiar with the toric code with topological phases of matter, et cetera. And these give rise to interesting quantum error correcting codes. But you can ask for codes that have better code parameters, like they encode more states, and those states are more resilient to noise than, say, in the toric code. The toric code is pretty resilient to noise, but it doesn't encode very many states, so you could try to do better. And there are now a growing number of constructions that do better. I won't define precisely what better means, but they do better. But the thing about these constructions is they typically live in this setting of sparsely connected graphs. Okay, so they're not fully connected. They're not geometrically local in the sense of Euclidean space. They're in this kind of sparse setting. And so I've been interested for a while to understand better the kinds of phases of matter, if you will, that you can realize in these sparse models. Maybe from the point of view of having interesting error correcting codes and connecting that to interesting many-body physics. So I don't think SYK really does this all the way, but I will show you some evidence that sparse SYK has code property in its ground space. And I'll give you a tensor network model that's in progress that helps us understand what this looks like. So this will be the very last part of the talk, which is very much in progress and speculation, but I'm happy to hear your feedback on it. And let me just mention before I get to the main part of the talk, just to orient you a little bit, what kind of things can happen on these sparse models? Well, one thing that can certainly still happen is symmetry breaking. So if you have an Ising symmetry, for example, or a U1 symmetry, that symmetry can still break. The breaking is similar to that in a mean field model. You would still have what con-mat folks would call a tower of states, but there's typically no Goldstone modes because these are associated with sort of spatial structure on the lattice. And the analog of the Laplacian on the lattice, which would normally control the spectrum of Goldstone modes, has a gap. So there are no low-lying modes, but there is a uniform mode. And this is relevant because that's how we actually will understand the emergence of gravity. It's going to be like a uniform symmetry breaking mode in this sparse model. And so the fact that you can still have these symmetry breaking phenomena is kind of sort of key. Yeah, I already mentioned this. There are these interesting novel codes with robust entanglement structure that arise in these context of sparse stabilizer models. I won't really talk about them, but that's definitely a motivation to think about this class of systems. And then I also wanted to mention, as I already pointed out, that there's still a notion of graph locality. You can talk about exponentially decaying correlations and so forth. And also in terms of previous literature, I'll mention that there is a previous work by Benson, Gu, and Lucas, where they studied models where you take clusters of SYK, so whole large N clusters, and put them on the vertices of a graph. That'll be sort of similar to what we're going to do, except that we're going to have just a single fermion on each vertex, and it's not going to be a graph, but a hypergraph. So there, that large N on each side gives you extra control, and we have to work harder to show our results. Okay, so here is SYK. I have a bunch of fermions, chi A runs from 1 to n. The dimension of the Hilbert space is 2 to the n over 2. I have an integer q, which I can choose, which is how many fermions participate in an interaction. And then I have a Hamiltonian, which is just a sum over all q-body interactions of fermions. So I sum over every possible pairing, or not pairing, but grouping into q. That's this sum over big A. And each has an independent Gaussian random coupling, which is independent of time. So I really have an ensemble of Hamiltonians here. The average of the couplings is 0 over this ensemble, and the variance has this standard form that depends on n in a certain way, so that thermodynamic properties are extensive. And there's, of course, a very large body of work studying this. I won't even try to mention or do it all justice, but this is the starting point. Okay. Now, what we're going to do is consider making this model sparse by deleting terms in the Hamiltonian, essentially. So in this model, there are n choose q terms, so roughly n to the q terms. We're going to just start deleting some of those terms. Okay, that's the basic idea here. So let me define what I call a pruned model, which is, and I'm going to use the q equals 4 case as an example. So here I have a sum over all possible 4 tuples of fermions, and I have my j, a, b, c, d coupling, but I'm going to produce and put a new number in there, x, a, b, c, d, and this x number is either 0 or 1. And the probability that that's 1 is p. So p is the probability that I retain this term in the Hamiltonian. And the average of the couplings j is still going to be 0, but now I'm going to change the variance a little bit. Okay, so what I'm going to do is I'm going to put a factor of 1 over p in the denominator. Well, I guess 1 over p in the numerator, or p in the denominator. And this choice here is not completely obvious, although you can guess it by looking at, say, simple Feynman diagrams, or by, again, demanding that the variance of the Hamiltonian is extensive. But anyways, you can make this choice here. And so it changes the couplings, the size of the coupling variance, right? And so now I have a new family of models where I decide what my pruning probability p is. And this family of models has an expected number of terms in the Hamiltonian, which is p times n choose 4. And this defines for me the number k. So k is the ratio of the number of terms to the number of fermions. And if p is just an order 1 number, like if p is a half or a fourth or something, you're just deleting some order 1 fraction of the terms, and it won't surprise you to learn that doesn't change things very much. What we're going to consider is the case where p scales with 1 over n, so that the number of terms is proportional to n itself. So this is an extreme limit where we're deleting almost all the terms in the Hamiltonian. We're retaining just enough terms to sort of have connectivity and no more. And this is what we're called the sparse limit. So here's that set again differently. If the number of terms is p times n to the 4th, roughly, then if we take n to infinity with k going like n cubed, that's the fully connected limit. That's where the number of terms scales much faster than the number of fermions. But we can also consider the sparse limit, where the number of terms scales with the number of fermions such that k is fixed. And so I emphasize again, this means that p goes in this case like 1 over n cubed. So you're deleting almost all of the terms. The probability to retain a term is very low, but there's so many terms that I end up with proportional to n terms at the end of the day.
A question?
Yeah.
Is it clear that this is the sparsest you can make it? Can you make k even smaller?
Yeah, so k can't be smaller than a constant, because if it's less than that, then the system breaks up into disconnected pieces.
I see.
Like if k scales to 0 with in any way with n, then at large n it will break up into pieces. So you have to have k at least be a constant, and yeah.
Thanks.
So the question is, well, the question will be whether a fixed k is enough, and then what's the sort of smallest value of k you can have to still get the interesting physics you care about.
Is there some kind of interesting percolation behavior at some threshold k?
Yeah, there is a lot of potentially interesting behavior, at least. I have to say we don't understand it very well. I'll show you some results later that suggest that could give you a certain value of k critical. There's also values, sort of critical values of k that come just from graph considerations, like if the graph breaks up into pieces. So there's sort of at the graph level, there's like kind of the dynamics level, and it's not clear like which one is the most important one, like which one occurs first. as you decrease k. So yeah, this is definitely an area where there's lots of questions and not so many answers. And it could be something pretty interesting there. Okay, now this random setup is nice for explaining, but in terms of doing analysis, it's actually much better to use a more regular model, because the random model has kind of fluctuations in the connectivity, which is not so nice. So what we can define is a model on a so-called Q-uniform KQ regular hypergraph. So what does this mean? Hypergraph is like a graph, except now instead of edges, you have hyperedges. And what a hyperedge is, it's a collection of a number of vertices. If you think about an edge as a collection of two vertices telling you what two vertices are connected, a hypergraph is a collection of some number of vertices, which tells you that those vertices all are together in one hyperedge or one unit or one interaction. So you can see this is a pretty natural language for SYK, because each four-body interaction is like one hyperedge. And we just specify the hypergraph by giving the set of all edges, the set of all hyperedges, which is the set of all interactions. And the Q uniform means that there is exactly Q vertices in each hyperedge, and KQ regular means that each hyperedge each fermion participates in KQ hyperedges. So each hyperedge has Q fermions in it. Each fermion participates in KQ hyperedges or interactions. If you go through the probabilistic analysis of this, and you compute the expected number of terms that each fermion participates in, that'll be proportional to KQ. So here we're just kind of encoding it as a fixed regular property of this hypergraph. And we can also restrict the hypergraph to be connected, so this will rule out clusters, small clusters, and that's a nice thing to do. If you've never thought about these hypergraphs before, you can think of them relatively simply in terms of an auxiliary bipartite graph, where there's two sets of vertices. One set of vertices is the fermions, and one set of vertices is the interactions. And there's an edge between a fermion and an interaction if the fermion participates in that interaction. Okay, so it's just these two kinds of vertices, the fermions and the interactions, and you have edges between them whenever a fermion is in an interaction. This is completely equivalent to the hypergraph model. So there's that. And so this is nice. It's a nice thing to study because it's very regular. We think we can have control over the pruned case as well, but the hypergraph model is easier to analyze. Okay, so before I go into the method of analysis, let me ask if there's any questions about the setup of the model or the motivation or anything like that. Okay, well, so now how can we analyze this model? Again, at the back of our minds, we're hoping or thinking or wondering if we can get the gravitational physics at low temperature out again. And so we historically approach this in a number of different ways. One thing you can do is, for example, establish that there's a 1/k expansion. So you can show that to leading order in 1/k, you recover the fully connected result. And then you can try to do a 1/k expansion. I mean, there is a 1/k expansion, and you can try to understand whether the corrections there are important or not. You can also just do numerics, which I'll show you some of it in a minute. But eventually we found what I consider to be rather elegant path integral approach, which is basically taking the usual path integral analysis and fusing it with the hypergraph structure. So let me review that structure for you here, and then show you where it gets modified to deal with the hypergraph. So the starting point for us will be n powers of the partition function averaged over the randomness. So far we're averaging over just the j randomness, so not the x's. The x's are going to be viewed as fixed. We're just fixing what terms are present, but we're going to average over the j couplings. You could also average over the X randomness. That's something we talk about in the paper. It's interesting to do that, and there are some interesting questions there which we haven't fully answered yet, but this is the nicest and simplest setting, I think. And I'm taking the replica index seriously here because we want to be sensitive to the possibility that there could be replica symmetry breaking, for example, or that there can, well, we want to be sensitive to that possibility. We didn't find any evidence for that so far, but actually because this model has extensive number of terms, a number of terms not growing within, there were a number of terms proportional to n, it turns out that the partition function is not going to self-average the same way it does in SYK. So in the language of disordered systems, the quenched and annealed approximations are not equivalent. Nevertheless, we'll get away with essentially looking at the average partition function. The effects which don't depend on that, I mean, for which that fails, are subleading for the questions we care about. But again, I would say we don't understand this very well. So let me just say again, the point is that since the number of terms is extensive, and since in that case, the variance here of each coupling is a constant, not scaling with n, the, say, variance in the average energy, the disorder variance, is extensive. It doesn't go down with n. And so the path integral itself does not self-average the way it does in SYK. So we should take replicas seriously, at the very least as a tool to get us the right averaging behavior of the partition function, to get access to the quenched approximation, which is the more physical thing for us. But nevertheless, it will turn out not to matter too much so far. Okay, so here's the path integral after that digression, where I have the fermion kinetic term, that's the first term, and the second term is the average over the J couplings, right? And A is the labeling of different couplings. XA tells me whether I have that coupling or don't have that coupling. So most of these terms are 0 in the sum over A, and alpha and beta are replica indices. Here's this replicated object, this 2Q fermion interaction. And then as usual, we're going to introduce these Lagrange multiplier fields that are going to substitute in for the coupling, I mean, for the fermion 2-point functions, for the fermion bilinears. And then we introduce some sigmas that are the Lagrange multiplier fields that enforce this constraint that G is equal to chi-chi. So far that's all standard, except we're not averaging over these XAs. And now what we want to do is we want to look to see, first of all, for saddle points. Can we find solutions of the equations of motion? And you can take these equations here, this path integral, write down the equations of motion. They look like the following. So first of all, we have a different Green's function for every site that's indexed by A. A is a fermion index. So there's a G sub A and there's a sigma sub A. So a fermion Green's function and the self-energy for each site. And they first of all satisfy this equation of motion on the left, which says that the inverse Green's function with the replica indices here is minus I omega minus sigma. So this is a site-by-site equation now, but otherwise it's the same as you'd have in the fully connected model. Okay, and then the self-energy equation is modified in an interesting way. So now I have the self-energy at some site A, proportional to J squared, that's the usual factor. There's a 1 over KQ, that's from the normalization of the couplings, coupling variance. And then there's a sum over additional sites or fermions. You have this weighting factor X, which tells you whether a given set of other fermions participates, and the Green's functions for all those other sites. So in other words, you look at a single site and you ask how many terms in the Hamiltonian connect that site to other sites. And the self-energy at that site is then a sum over all those other interaction terms weighted by the Green's functions on those other sites. So in other words, it's like just like a kind of Laplace equation. It's seeing the Green's functions on all of its neighboring sites, and that's what determines the self-energy. Okay, so fine, those are some nice equations of motion. We can try to solve them. The simplest thing to look for would be a uniform solution, a solution which every site is the same. It turns out because of this hypergraph regularity condition, which I've written here, which just expresses the fact that the number of terms that each fermion participates in, the number of interaction terms, is KQ. I mentioned that before. This regularity condition immediately implies that there is always a uniform solution, where the uniform solution, let's say if I also have a replica diagonal uniform solution, then the Green's function inverse is minus I omega minus sigma. That's the usual equation for a fully connected model. And the self energy is J squared times G to the Q minus 1. That's both the standard equations you get in the fully connected case. Okay. So at the level of the saddle point, what we've shown so far is that there is a solution to the equations of motion where the solution has exactly the same, like identical form to the fully connected case. And it's uniform on every site. I'll just mention here, we discussed in the paper, if you don't have the regularity condition, but you have just a random graph, then you can still look for solutions like this, but where you have a like weighting factor on every site that sort of, in our thinking, tends to uniformize things in some way. So we can't always show that there's a solution to that more general equation, but numerically there seems to be. So we think that this line of thinking morally also applies to the randomly pruned case, and we can at least establish that that's true numerically and in certain limits. Okay, so the regularity condition does seem to be just a convenience and not an essential condition. Okay, but as I said, unlike in the fully connected model, here the fluctuations are a lot bigger. That's true both for the disorder fluctuations, but also for the fluctuations around the saddle point. These fluctuations are no longer suppressed by n. They can contribute an order n amount to the free energy. So we have to take them seriously, and we have to understand their effects and whether they modify the saddle point's picture in any way. Okay. In other words, just think about you're trying to analyze a spin chain. That's, I mean, not the same, but sort of similar in spirit. You know, you want to find solution of the equations of motion, and then you want to look at the fluctuations around that and make sure they don't destabilize that solution. That's kind of the logic here. Okay, so we can look at the fluctuations easily enough. Where again, because we're starting from a replica diagonal saddle point, the replica structure is relatively simple. The diagonal and off-diagonal modes decouple. It turns out the off-diagonal modes would contribute to the free energy in such a way that it would make a difference between the quenched and annealed free energies. But somehow their contribution is very trivial at the quadratic order, which is all we can do so far. So I'm just going to ignore the off-diagonal ones and focus on the diagonal fluctuations. I'm happy to talk more about that later if you want. And from those diagonal fluctuations, you have this Fermion determinant, first of all, really the Pfaffian, but written here as the determinant. That's standard. You have the Lagrange multiplier term, that's standard. And then what replaces yeah, so this then is like the interaction term here, written in terms of these Green's function fields G. And we're going to look at fluctuations parameterized in the following way. This is not super important. I mean, nothing will depend crucially on this. It's just a nice choice to normalize the delta G's with this factors of G inverse. This is the saddle point solution. So we do that normalization, and what you find then at the quadratic order is something like this. There's a coefficient out front. There's a sum over pairs of sites or pairs of fermions. There's a delta GA, delta GB, so it's quadratic order. And then what does the structure inside look like? There's two kinds of indices. There's sort of time indices, and there's graph indices or hypergraph indices. So the AB are hypergraph indices, whereas the tau's are time indices. K inverse acts non-trivially on the time indices, but does nothing to the space indices, the graph indices, whereas MAB acts non-trivially on the graph indices, but does nothing to the time index. So this is one of our sort of technical results, key technical results, is that the quadratic fluctuations have this kind of factorized structure where there's one piece, the kernel K inverse, which is exactly the same kernel as you'd get in the fully connected model. And it has a sort of trivial graph structure. And then there's some graph piece, which doesn't care at all about the time dependence from the fully connected model. And these two pieces together tell you the quadratic spectrum of fluctuations in the model. And again, now regularity plays an important role because regularity ensures us that M over 12K, this matrix here, has a uniform eigenvector with eigenvalue 1. Okay. So you can replace this M over 12K with just 1 if you assume that delta G is uniform. And as you may know from the theory of SYK, this K inverse minus 1 is exactly the quadratic fluctuations of the uniform mode, of the fluctuation mode in SYK. Okay. So the mode which is uniform over the lattice, the fluctuation that's uniform, exactly recovers the fluctuations of the fully connected model. Okay, so we have those fluctuations there. That's what we want. Those fluctuations will what give you gravity at low temperature. What we have to ask now is whether there's other solved modes. If mode is gapped, we're fine with it. That means it's not going to change the thermodynamics or the dynamics significantly at low temperature because it'll be suppressed in the path integral. But if there's other soft modes, then we have to be worried. Okay. So to look at that, what we're going to do is we're going to focus on the low temperature regime where this SYK kernel has a certain structure. And we're going to ask essentially whether there are other places where the eigenvalues of K inverse touch eigenvalues of M. And if they only touch this one place where M has eigenvalue 1, that's the uniform mode, that's the one we want. If they only touch there, then we're happy. That means there's no other solved modes. And that's indeed.
So Brad, can I ask, sorry, I missed that.
Yes.
So if you take the soft eigenmode of K inverse, how does M act on it?
M just does nothing to it. So this K is really only acting in the time indices, and M is only acting in the like space or graph indices.
So what does the second term change the eigenvalue?
It does not, because there is this. So essentially, there's now a tower of modes, which have eigenvalue. If you thought of them as you know just SYK like modes, they have eigenvalue K inverse minus the eigenvalue of M. And so what I'm saying is there's one special mode where eigenvalue of M is, or eigenvalue of M is over 12K is 1, and that's the same, literally the same action as the quadratic mode in SYK. And then there are other eigenmodes of M, which have some other eigenvalue here, but now they're not solved anymore, so they don't affect the low energy physics.
Oh, so the mode whose eigenvalue of M is 1, that doesn't change doesn't make the soft mode doesn't gap the soft mode?
No, it does not. Like this for full SYK, this would normally be K inverse minus 1 here.
Okay.
That's what you have inside of the brackets. Okay. And so when we get this M is equal to 12K, that just recovers the usual.
Okay, all right.
All right.
I have another quick question about this.
Yeah, please.
So do all the eigenvalues of MAB scale with K? Like, is that K dependence just going to drop out with all the eigenvalues?
No, it does not drop out. I mean, so most of them will depend on K in some way. I'll show a picture actually in the next slide, I think. And in particular, as you take K large, the eigenvalues of M all concentrate near 0, except for this one special eigenvalue of 1. And this concentration is another way to sort of see the recovery of the fully connected physics.
I see. Thanks.
So yeah, so it really comes down to the spectrum of this M matrix. If there are other soft modes, there's always one soft mode, which is the one we want. If there's other soft modes, then we have to think about their physics and understand what they're doing. And what we're going to show is that the randomness, like taking hypergraphs randomly or doing the random pruning, has the effect of putting a gap in this matrix M in such a way that only the uniform mode is solved and all the rest are gapped. So here's a picture of that. So at low temperature, the spectrum of this K kernel is known. The spectrum looks like the following. Starting down here, I hope you can see this kind of light pinky red band. Starting at a negative eigenvalue, there's a continuum. There's a spectral continuum, which starts a little bit above minus 0.5 and goes down to negative infinity. And then starting at 1, there are discrete eigenvalues that start at 1 and go up. And so there's kind of a big hole in between 1 and something around minus 0.5 where this K object has no spectrum. Okay. Now you look at the spectrum of M, the M matrix. It has this one eigenvalue at 1. Okay, so that's where the overlap occurs. And then the rest of the spectrum of M now depends on K. K is the x-axis here. And as you increase A, you can see, as I said, that the spectrum starts to concentrate near 0, except for this one mode, always at eigenvalue 1. And so the fact that there's this gap between the spectrum of M, this blue part, and the lower continuum band down here at the bottom, and the rest of the spectrum of K above, means that none of these other eigenvalues of M overlap the spectrum of K, and so they don't ever contribute soft modes. If I go back to this thing, I need the spectrum of M to overlap the spectrum of K inverse in order for there to be a 0 here and me to have a soft mode. That only happens at this one place where the uniform mode of A has eigenvalue 1, then the kernel K inverse also has eigenvalue 1. That's the uniform mode. That's the SYK special gravitational mode. We then have to go to the next order in perturbation theory, and that's where you get the Schwarzian action from. So that all works out the same. And this picture is showing that there's no other modes that are soft, because these spectra just fit inside of each other in a nice way, and they don't ever have any overlap. It's interesting, actually, that you need not only to control the gap between the upper mode and the lower mode, like if this gap was small, then you'd have a lot of other continuum modes. So if, for example, you had, instead of a randomly connected sparse hypergraph, you had a 1D chain of Majoranas, there would be no gap here. There'd be a quadratically dispersed, there'd be no gap, and it would be associated with the Laplacian on a chain. So you'd have a whole set of low energy states coming from low momentum modes, different K. But here also, actually, we need to make sure that the lower part of the spectrum doesn't overlap with the continuum of negative modes in K. There are actually models where you can get instabilities because you have like an eigenvalue that lives inside this negative continuum here. But that doesn't happen in our case, at least for modest values of K. And so at the quadratic level, we conclude then that the only soft mode is the Schwarzian mode. All the rest are gapped. And it's pretty remarkable that this actually holds down to quite low values of K. So even K of order 1 or smaller seems to work. And in fact, if you look at the structure of these Laplacians, it seems like it even will work down to K of order 1 over Q, which at the level of graphs is like the lowest it could possibly be without disconnecting the graph. So we don't really know what the smallest value of K is that gives you this physics. You know, it could be that high order fluctuations modify this picture a little bit. But at least for K of order 1, say 2 or 4, it looks very robust. Okay. So the conclusion of the analysis then is that we have this one quadratic mode that will turn into the Schwarzian mode that we want. Its action is unmodified, at least at quadratic order. And all the rest of the modes are not soft, they're gapped. And so we don't expect them to modify the infrared physics. Okay. We can't do more than this at present. We can't, we looked a little bit at the next corrections, but there was no simple story there. So this is the status of the analysis at this time at the path integral level. I did mention that there is a 1 over K expansion that one can pursue. That's interesting, but we didn't follow it very far, and I think this is a cleaner argument. Okay. And you know, to summarize, the basic physics here, I think, is that this gravitational mode comes from a certain pattern of symmetry breaking. There's an emergent reparameterization symmetry at low energy, and that symmetry is broken both explicitly and spontaneously in a certain way. And what's happening is that we are still having that pattern of symmetry breaking occur even for the sparsely connected model. And as I emphasized in one of the introductory slides, that's a phenomenon that's known to occur in these sort of models. And so it sort of seems sensible. Like basically, it's the global uniform mode, which is the interesting mode. You still have that symmetry breaking, so its physics is still the same. And the Goldstone modes or other would-be modes that would cause problems are all gapped because of the structure of this interaction graph. Okay. So now let me talk to you a little bit about simulations. This is sort of the practical side of things. Here I'm showing some numerical simulations using a Krylov technique where we're looking at 52 fermions. Actually, there's several different curves here, but let's just look at the left-hand figure for starts. So I have Q equals 4 body interactions. I'm plotting the entropy of the system versus temperature. I get the entropy by measuring the average energy relative to high temperature and integrating down. This is a standard technique. And in black is the mean field answer. That means the infinite n answer that you get from solving the Schwinger-Dyson equation. And then blue and red are n equals 52 with two different values of k equals 4 and k equals 8. And then green is n equals 40 with k equals 4. So the first thing to notice is that, of course, they all agree perfectly at high temperature. That's not too surprising. That just sort of means we normalize things correctly. Certainly 40 is different from 52, but actually different values of k at 52 are on top of each other. You can't tell them apart. This red line actually has a blue line under it, but they're just identical. So the value of k actually makes almost no difference throughout thermodynamics. And I have to say, I think we don't understand why this is well yet. I mean, I gave you an argument that I believe for why the sort of universal part of the thermodynamics at low temperature is not changed. But why it seems to be so robust over such a wide range of scales is not so clear to me. So in other words, it seems to be better than we thought or had any reason to expect at matching the fully connected result. Okay, so that's something we don't, we can quantify the deviation and it makes sense, like using diagrams, but I think we don't have a deep understanding of, how big the deviation can be. But anyways, you see here also that down to relatively low temperature, it just matches the mean field value quite well. And then at low enough temperature, you start to see finite size corrections. The fact that blue and red curves are the same means there's not really a finite k correction, but there is a finite size correction. And so here in this inset, we're plotting it now at lower temperature, smaller values of log beta j. And the black is the mean field, and the blue is what we get from our data. And this dashed line is the next 1/n correction to the large n large n free energy, which has a very characteristic and universal form. And actually it's approaching the slope of this line, which should be a log of temperature pretty well. Okay, so we didn't go down super low temperature, but it seems reasonably convincing. We can also look at correlations as a function of time. At high temperature, we can clearly see exponential decay with a slightly different slope than you would expect from the fully connected model. Not 100% sure what this deviation is. We can also see low temperature, a sort of slower exponential decay as you would expect. That's all nice. So this is 52 fermions, which, as I said, sort of was a state of the art when we started, but was later surpassed for the full model by this study of Coburn et al., where they looked at 60 fermions. There is a huge difference in the computational effort involved, with these results requiring much less, but nevertheless, we haven't pushed it yet to larger numbers. If there's an interesting question, it could be interesting to push it. But one thing we can do is to look at larger Q. And I think this would be essentially impossible for, say, 52 fermions for a fully connected model. But here we can do it relatively easily. So here I'm showing you Q equals 8. So 8 body interactions, again, mean field. I'm comparing k equals 4 and 8 at 52 and n equals 40 with k equals 4. The same thing is roughly true. You see there's definitely a finite size effect, but very little finite k effect. And now if we look in the low temperature regime, we see a remarkably good agreement between the prediction for the correction to the free energy, to the entropy in this case, with the 1/n correction that you would get from the large n theory. Okay, so the slope is just perfectly the same, which is really nice. And I'll just mention, this is like just incredibly effort saving. The fully connected model at Q equals 8 would have about 750 million terms in the Hamiltonian. That's 7 times 10 to the 8. This sparse model for k equals 4 and 8 has either 200 or 400 terms in it. Okay, so the amount of time you save, because these methods work just by applying terms in the Hamiltonian repeatedly to some vector, is enormous. And nevertheless, you can, if that's your goal, access very similar physics to the fully connected model. And if you want to do something else, you can study this sparse model on its own as its own interesting thing. I'll also mention, this was another one of our starting motivations, which I already discussed with you previously. We were interested in sort of how efficiently can you simulate gravity holographically using a quantum computer. So previously it was classical simulation. Now we can also talk about quantum simulation. The prior best I already discussed with you was for this Q equals 4 model. And now our new results are that you can do this much more efficiently, especially at large Q. We did what's called a qubitization approach, which reduces the complexity for the SYKQ model from this n q plus 3 over 2 to just n squared independent of q. And also product formula. So this is like trotterization simulation. You can get even better scaling with n as long as you don't want to go to too long of time. So this is actually almost linear scaling in some certain regimes with n, which is the theoretical best you could possibly do. And now the log is really coming just from the fermions. It's a very efficient fermion encoding, but we still have a log overhead. So we're sort of now approaching sort of the theoretical best that we can do. And so if you want to go out and simulate quantum gravity on a quantum computer, this is actually the best way to do it. I won't talk about this, but you can do everything I said for supersymmetric models as well. Originally studied by Fu, Gayoto, Malasena, and Sachdev. Now you can sparsify the supercharge instead of the Hamiltonian. It still has exact supersymmetry. Many things are similar. And yeah, you can do some numerics and see that it agrees well with what you expect from the large N theory. I mentioned this for 2 reasons. One, it's going to show up again in a second. And because there's greater theoretical control over the sparse SUSY model. So we kind of started there for a while thinking about that. And then eventually we understood better just the non-SUSY case and focused on that because it was simpler. But this is still a very interesting situation, and I think essentially unexplored, these sparse supersymmetric models. Okay, so let me wrap up. One thing which is interesting about this project is that for me, it changed what I considered to be a sensible mini-body system. So if we were in person, I would take a poll of everyone. I won't do that here, but you know, there's an interesting sort of quasi-philosophical question about what you consider to be a legal mini-body Hamiltonian. Like what are we allowed to study in the subject of mini-body physics? And I think this sort of standard answer for me is a theorist answer is any few-body Hamiltonian is essentially allowed. But we don't want the number of terms in the interaction to scale with system size. That's usually not sort of, we might think about it, but it's not sort of a good model of reasonable systems. And so in particular, you know, as Q increases in the full model, the simulation cost goes up. You have these more and more high body interactions. But as we saw, when you have sparsity, then you get this bigger and bigger reduction in the simulation cost. Now at fixed K, large Q also pushes us closer to the fully connected limit. And people had in the past considered various, what I'll, with no ill intent intended, call unphysical limits, where you take Q to scale with n in some way, like Q goes like square root of n. But these would require super polynomial resources to simulate in a fully connected case. So in other words, you cannot do a simulated experiment on them with polynomial resources. So what I'd like to say is my sort of new point of view is that, well, what makes a system legal to think about? Of course, you can think about whatever you want, but you know, what makes a system reasonable? Well, it's reasonable if we can simulate an experiment on it with reasonable resources. I think that's a reasonable thing. I mean, we don't have to require that we can actually dig it up out of the ground, but we should be able to play with it in principle in our quantum computer. And so that would just require that we have some polynomial ability to simulate, that system with polynomial resources. And whereas you could not do this with the fully connected model with Q scaling with n, you can do it in the sparse model. So actually, from this point of view, there's sort of a new, slightly bigger class of systems that you couldn't think about or couldn't simulate before that you can simulate now. And yet we think that the physics in many ways will be very similar. So it's a sort of interesting expansion in my mind of what I consider to be a reasonable many-body system. And there, may be some application of this. For example, there's interesting thoughts about large Q being related to Schwarzschild black hole instead of near extremal charged black holes in the gravity context. And the other thing I'll mention, just by way of passing here at the end, is about these codes. Okay, so here is some numerical evidence that the ground states of, in this case, the supersymmetric model form a code. So I've taken a bunch of ground states, I've taken a simple operator O, and I've looked at the matrix elements of that simple operator between these different ground states. And what you see is that there's a strong diagonal, which is what you can't really tell very easily, but it's pretty uniform. And then the off-diagonal elements are nearly zero. So this is the standard criterion for quantum error correction, that you have a set of states, code states, that cannot be distinguished by a simple operator O. And that's what this picture is saying. Okay, so this is some numerical evidence, but we really wanted to understand better, like, what's the picture of these states and how these states work. And so in ending, I'll flash an idea for a tensor network model of the ground states of this system, which looks like the following thing. So it's going to be composed of layers. If you've ever thought about a Mera tensor network, this is somewhat similar to that. So we're going to have two kinds of degrees of freedom, roughly. We're going to have n0 degrees of freedom, say qubits. I won't worry about qubits versus fermions in this case. Say qubits here, which is the log of the ground state degeneracy. So it's like the number of qubits you need to represent the ground state space. And then we have some active qubits that are growing between layers. So we say put in at the bottom 2k qubits and we get out 2 to the k plus 1 qubits. And these layers are going to be some kind of roughly constant depth circuit, but they're not going to be geometrically local. So like everyone can talk to everyone. So you can think of it just like evolving with some entangler, which looks sort of similar to SYK for a unit time. And the idea is we're going to build up the full set of states in the system in this hierarchical fashion, where we start down here at the bottom with the ground state space and say 1 or 0, input qubits here. So that means if you cool a system down to the low energy, you just have the ground space. But then as we go up, we double, and this is an accurate doubling. I actually used PowerPoint to do this correctly. So it doubles the size up to the right of this dashed line at every step. The number of active degrees of freedom is doubling every time. So whereas in Mera, the whole number of degrees of freedom was doubling every time, now we kind of subtract off this ground state part and then double and then add it back and repeat. Now I'm making this distinction. It's actually artificial. The circuits don't distinguish the input lines on the two sides of the dashed line. But what this representation can do is it can first of all capture the entropy scaling and the thermodynamics as a function of temperature. If you assume that the Hamiltonian, when it passes through one of these layers, is like a scaling variable. So again, very similar to Mera. So it can reproduce complexity estimates from gravity. It can reproduce entropy and thermodynamics. And it can reproduce a number of other crude properties of the spectrum. And what it also tells us is something about, if this is really a model of the ground space, it tells us how information is encoded. So you can think about putting information in at the bottom, encoding it by passing it through this circuit to map it to the UV, to the cutoff here at the top, where it's been encoded in some complicated entangled state of all these fermions. And so, for example, you have an extensive number of qubits that you can encode down here. They're encoded in some larger number of qubits here, but it's extensive encoding. So the number of encoded qubits is proportional to the total number of qubits. And moreover, if you have some operator here that distinguishes them, some logical operator, it's spread out by this circuit in such a way that it acts on order n number of degrees of freedom at the end of the day. So what this picture suggests is that if this code idea is correct, and if we can make this precise, then it could be that we have a sort of approximate code in the ground space where the number of encoded qubits is proportional to the total number of qubits with some coefficient of proportionality less than 1, but constant at large n. And the logical operators, that is the things you need to act on to change these encoded qubits, also have weight proportional to n. So this is actually kind of the best you can hope for code parameters. It's typically a very good code in many ways. We don't, and this would all be coming from the ground space of a local Hamiltonian. Okay, so this is just a picture. We don't really know if this is the right picture yet, but it's a picture. We can certainly take this kind of architecture and make artificial codes from stabilizers, for example, which have interesting properties. But whether this is the right picture of the SYK ground states, we don't know yet. But it's a conjecture, an unpublished conjecture, but a conjecture. Okay. And if so, it gives us, if this is really close to the right picture, it gives us a new perspective on what these ground states look like, maybe how to map, how to connect the SYK to the emergent gravity. You might think of this radial direction as like the gravity direction, similar to the Mera gravity correspondence. And so it's an interesting thing that I'm very excited to be thinking about right now. Okay, and with that, I'll summarize. So I told you about essentially a procedure, a machine you can apply to whatever your favorite fully connected model is. SYK, Heisenberg, TJ model, anything you care about, you can sparsify it like this. And we think that's an interesting class of models. It has a lot of benefits from simulation point of view, and it's interesting to think about the physics. In this case of sparse SYK, we argued that you still get the gravitational sector at low energy. I also showed you that sparsity gives really major benefits for simulation. And kind of a fun little thing, it gave me a new perspective on what it means to be a sensible quantum minibody system. And as I hope I convinced you at the end, there's a lot of interesting directions to explore. I'm particularly interested in this code point of view, but implementation, maybe novel classical simulation methods. For example, you can simulate systems on trees using tensor networks in various ways. So you could try to actually do like a simulation of SYK, sparse SYK using the tree structure to do like a large N simulation. That could be quite interesting. There's quite a few directions here. But with that, I'll say thanks, and I'll flash up here some other work by people in my group on related topics, and say thanks and take your questions.
Thanks very much for the talk. So as usual, we won't place any time limit on the questions, but maybe it might be good to start with higher level conceptual questions if people have any before we get too much into the weeds. So yeah, open for questions.
I was actually wondering, what do you think would be the most useful outcome of being able to simulate gravity in this way on a quantum computer? Like, what would we learn by doing that? What can we hope to learn?
That's a great question.